Hello everyone, welcome to week 1 of Biochem. I'm going to do a little mini lecture to kind of get the course started and answer some of the questions that you guys have been emailing me about. So to start off, I'm going to talk a little bit about amino acids and why we even have L and D versus R and S. If you take a look at an L amino acid, such as... And a cat just ripped off half my desk. This alanine here. If we're using our normal R and S naming, we would put this nitrogen as our highest priority, and then carbon attached to oxygens as our second highest, and this methyl group here as our third highest. This would give us a S stereocenter. The reason that we have L and D versus R and S stereocenters is that because this works for almost all amino acids, in the case of cysteine, when we do our priority, nitrogen is still first, but in this case, this carbon attached to sulfur is now a higher priority than the carbon attached to oxygen. So this is actually an R stereocenter, even though it has the same configuration as what we think of as an L amino acid. So to simplify this, they chose to make all amino acids where your nitrogen is coming out and your carboxyl group is on top, considered to be L amino acids. You can draw this in a Fisher projection. So if I take this guy here and I look, I'm just going to redraw it. If you take this and you look down the middle of this bond here, so this nitrogen, I'm going to circle, is going to be coming up at you on the left, versus this hydrogen here is going to be coming up at you on the right. Your carboxyl group will be going back in the top, and your side chain will be going back on the bottom. And that would look something like this here. And we can draw in wedges and dashes to kind of elucidate that. So, anytime you have this carboxyl group on top and your amino group on the left, this is considered to be an L amino acid. And then to draw D amino acids, you just flip your H and your NH3 here. And now we have a D amino acid. So when we have these amino acids, there are these various charge groups on them. And depending on the pH of the solution, that is going to influence the protonation state of your molecule. So there's two different main protonation states that we deal with in biochemistry. You're dealing with nitrogen and oxygen, and it's going to be nitrogen that is positively charged. I'm going to draw just an R here, going to a nitrogen that's neutral. And this has a pKa of around 10. So what that means is that when your pH is below 10, so say you're at pH, capital H, of 7, you're going to be in this range here, versus when you're at a pKa or pH of around 12 or above your pKa, you're going to be in this range here, where you have a nitrogen that is neutral. There are other pKa's for nitrogen. For instance, you could make NH minus, but this pKa is around 35, which is way off the charts for anything you're going to be doing in this class. The other one that you're really going to be dealing with is going to be this carboxyl OH here. So this OH has a pKa of around 4. And I'll draw the other. So when we're in a solution who has pKa, or sorry, pH is less than this, we will have the proton on your oxygen, and then when we are in a solution that is higher, like 7, we will not. 1 second, blow my nose. Okay, so how does this affect a full amino acid? So let's pull up just alanine. So we often draw amino acids like this here. So this is what we call the zwitterion, which I'm going to attempt to spell. And this is where you have a negative and a positive, but you are overall a neutral compound. This happens around pH 7. But as you may have noticed, we have both a nitrogen and oxygen in this compound. So depending on the pH, we can either pass one or both of the pKa's. So say we go to a more acidic solution. So if we're in a pH of 2 solution, if you remember, I'll write out the pKa's. This pKa is around 4. This one is around 10. So we're already way below 10 at pH 7, but if we go all the way down to pH 2, we're also below this pKa 4. So that means that we are going to gain the proton on our carboxyl group, giving us this overall positively charged molecule. If we go in the opposite direction, now let's do pH 12. So at pH 12, we are obviously above pKa 4, and now also above this pKa of 10 here. So we're going to lose the proton, which we already lost from the oxygen, as well as a proton from this ammonium here. And this is going to compound which is going to be overall negative. So this one over here was positive at low pH because we have this group here, and then this one at high pH is negative. So if you have a side chain that has a pKa, so let's take lysine for example. I'm going to start off by drawing your normal 1, 2, 3, 4, 1, 2, 3. pH 7 solution here. So now we have 2 amines, and both of these have pKa's around 10. And again, this pKa for this carboxyl group is around 4. So now when we drop to a pH of 2, we're already below pKa of this guy here, so now we're only modifying this carboxyl group. Switch back to black. So we're going to end up one more. With this compound, which will now have a positive Chu charge, because we have a charge on each of these nitrogens here. Also worth noting that we started out with these two will cancel each other out, so we're just left with a positive 1 charge on our starting lysine. So now when we go to a high pH, like pH 12 here, we are going to lose the proton on both of our nitrogens. This will give us NH2 and NH2 here, and an overall negative amino acid. This starts to get a little bit more complicated when we get into peptides. Whoops. So, peptides in general, I'm going to start from the N to C terminus. So, like an amino, well, you're building amino acids from each other. So I'm just going to take 2 amino acids and put them next to each other to start with. To give you kind of a sense of where they come from. So the basic concept is that in a reaction, and I'm not going to draw all the steps, your amine is going to come in and displace this oxygen, and you're going to form what looks like this here. And I'm going to circle them in other different colors. So this blue amino acid is represented here. and our green amino acid here. Okay, so positive charge there. This would be considered a dipeptide of 2 alanines, so ALA, ALA, or AA. Oh, sorry, my nose is running today. Okay. Let's see what else. With these peptides, and I'm going to draw a little bit more complicated one, and then talk a little bit about. So I'll do just a big naming one first. So let's say they give us, I don't know, they want serine, alanine, aspartate, and glycine. So we're going to start with just a peptide backbone. We need 4 amino acids. So this would be amino acid number 1. I'm going to draw the next one in a different color. Amino acid number 2. Amino acid number 3. And amino acid number 4. From here, we need to add in our side chains. So our first one was a serine. So we are going to have a CH2 and an OH. The next one is an alanine. So our side chain is going to be a CH3. Our third one is a aspartate. So we need, whoops, I drew a D amino acid there. There we go. Aspartate. So CH2 carboxylate. And the last one was glycine, which means we just need 2 protons. So the way I like to do these is you draw out your backbone like I did before, and then from there you just fill in your side chain with whatever you individually need. The last thing I'm going to talk about is peptide charges. So this is similar to amino acid charges, except now we have a larger molecule. So I'm going to do 2 different tripeptides. So let's see. So we need 3 amino acids. Giving us this here. I'm going to do serine, aspartate, alanine. So just looking at our, I'm going to start with pH. pH 7. I can delete. There we go. pH 7. So our peptide backbone, we have both a positive and a negative here. So your overall charge is going to be neutral for your starting out with. And then as you start adding in your side chains, this may affect this. So serine, like before, is just an OH. Aspartate has a carboxyl group in it. So now you may notice we already have a second negative here. And then our last one was just alanine. So now if we're adding up all of our charges, we have 1 negative, 2 negative, 1 positive. So our overall charge is going to be -1. Now, if we drop this pH to say 2, just going to redraw the backbone. Hopefully I don't run out of room. And these ones both don't have pKa's. So now, oh, sorry. I want to get rid of this guy here. So now we're at a pKa of 2, or pH of 2, which means that this one will be protonated because this pKa was 4, as well as our aspartate is also going to be protonated because that pKa is also 4. So now the overall charge on our molecule will just be this nitrogen plus over here, because this one is neutral and neutral. So at pH of 2, this molecule has a charge of +1. And I'm going to draw the next one on the page because I'm going to run out of room. So at pH 12, not 112, pH 12, we are going to lose the proton from this nitrogen, so that will be neutral. Our unaffected side chains stay the same, and then at high pH, both your carboxylates are going to remain as negatives. So for this molecule here, you have 2 negative charges, so the overall charge, is going to be -2. I'm going to do one more. So I'm going to do one with a lysine on it. So sorry, drawing these as fast as I can. Let's put a lysine here. 1, 2, 3, 4. 1, 2, 3, 4. NH3. And then I'll do a valine and a, I don't know. I'll just do another alanine. So if I was naming this, this would be a lys, val, ala, or KVA. Alright, so starting out with, at neutral pH, pH 7, that is a 2, pH 7, we are going to have 2 positives, 1 negative, so our overall charge is going to be +1 here. If we drop the pH down to negative, or not negative, hopefully not negative, pH of 2, we're going to end up protonating our terminus. Over here, so now this becomes OH. We retain our two amines over here, so now our charge on this molecule is +2. And then our final one at pH of 12. We're going to lose the proton on our nitrogens. Oh, no, I have to remember what I drew. It was a valine. This one kind of looks like a face. Okay, so now we've lost both of our charges over here. These are both neutral, and we're left with just this minus here. So that gives us an overall negative charge on this molecule. I hope this was helpful. If you guys have any further questions, please send me an email, and I will get back to you as soon as I can. Hope you guys are enjoying the course so far. Expect to see the next video around beginning of next week. Best of luck, guys.